When you look at the architecture of these systems, you know, Willis Carrier made the first commercial air conditioner back in 1902. And a lot of the systems you see today have a lot of similarities to those systems that, were built 50 or 60 years ago. But there's a lot that we don't understand, that we need to understand to really improve the performance. One project that we're working on right now relates to these heat exchangers, for example. And here's a good example of one. This has been a piece of a heat exchanger that we have in our systems. And you'll see that the tubes in the heat exchanger are these straight tubes. Well, one of the trends that we have in air conditioning systems is that people want to make them smaller, right? You want air conditioners that don't take a whole lot of space in your house. But as you try to shrink this, you start to run into fundamental physical limitations for what the heat transfer can be. So we have a number of projects that are trying to really improve the sort of mechanics of exactly what's going on inside these systems, both at a component level and at a system level. So one project that we're working on is where we're actually looking at how do you improve mixing in these channels. Basically, for heat transfer, you really want to have good mixing throughout the channel. But as you shrink these channels, it goes to a flow regime, a region of flow where you don't get a whole lot of mixing, and the performance actually goes down as you try to make them smaller. So we're looking at some ways of actually optimizing the geometry, improving exactly what the structure of the fluid flow is in here, so that you can keep shrinking it without paying the penalty of heat transfer of reduced performance. And so what we would expect is that this system, which is in the commercial systems that you can buy today, will be able to continue shrinking them without being penalized, and that's going to be a really, really big benefit. Another aspect that we're working on a system level, so this is on the component level, on the system level, we're also looking at adjusting the amount of refrigerant in the system. What happens today is that when you put refrigerant in your air conditioner, we sell these systems all over the world. You might sell them in Dubai, you might sell them in Atlanta, you might sell them in Minnesota. For every single one of these type of systems, it'll have the same amount of refrigerant in it. But the efficiency of this system is a strong function of the mass. So in Minnesota, you might actually want to put a little bit more refrigerant in. In Atlanta, you might want to put a little bit less refrigerant in, and that's not done today. So we're working on technology that actually changes how much refrigerant is in the system based upon local conditions. It's going to change it based on if it's in heating mode or if it's in cooling mode. It'll change it based upon whether or not it's a hot day or a cool day, and you can get much better performance. You can optimize the performance of the system in a way that you couldn't optimize it without changing the refrigerant mass. And so these are a couple of different areas that we're really working on improving the system, improving components to get performance where you wouldn't be able to achieve it without these sort of research results. The trick is that the systems are very sensitive. These systems have a lot of spatial dependencies, and understanding what the sensitivity is. If you put too much refrigerant in, your performance is going to also be lousy. So it's not about putting a lot of refrigerant in or just a little bit of refrigerant in. A very, very small change, on the order of, for this system, maybe 50 grams, can make the difference between really good performance and really bad performance. And so the high sensitivity of these systems makes them very hard to engineer. And very challenging. I mean, this is why these systems haven't been sort of developed, and why there's still a lot of research to do. And one of the things that is so exciting to me about working at Merle is we really get to sit down and think hard about this complex, spatially, temporally distributed physics, and do computation to understand how to really squeeze the most performance out of these systems that people haven't been able to do. And it's only by leveraging all the computation and mathematics that we have at our disposal here at Merle. In the HVAC team, there is a lot of different expertise, and it's interesting to me that all of these different people are needed to really accomplish what seems really like a very simple goal, and that's what's needed about it. Residential air conditioning in 2009, air conditioning and heating systems consumed 4 quadrillion BTUs of energy at a cost of $95 billion, and represent about 40% of the energy consumption of houses, of residences. Okay, so it's a huge amount of energy at a huge cost. If that's going to be, this is a number that doesn't typically go down. So if we can sort of bend the curve over, and this is going to take a lot of work, both on sort of the mathematics, the experimental, and the physics side, as well as trying to spread these innovations throughout the industry, because it's just a drop going in, but what we're looking for is that diffusion effect. If we can even make a small change in 4 quadrillion BTUs per year, that ends up having a really, really big impact. And that's what we're really going for here at Merle.